So in this video cast, we're going to go over some buffer problems from Chapter 17 and learn how to use the order of events for problems in Chapter 17 to hopefully solve a number of this worksheet's pieces. So make sure that you have this worksheet on in front of you, calculator and pH square and a periodic table piece, probably something like this, to help you along the way. So starting with number one, suppose you have a solution that has some HOCl in it. And first of all, it says calculate the pH of the solution. So this is a problem you did back in chapter 16 because all we have is HOCl in the solution. This is what's known as a weak acid. How do I know that? Because it's not a strong acid, and remember you memorized the strong acids as hyperhickel high, honohickel OH2SO4, and anything else that has an H in it like this, starts with an H, is going to be a weak acid. So I've identified the weak acid or base, and now write the equilibrium of the weak acid or base with water. And so I'm going to take this and react it with HOH. I'm going to donate a proton, because that's what acids do, and I'll have some H3O plus and some OCl minus. Once I've written the equilibrium of the weak acid or base, now I write the ice table, and in this case I only have molarity, so I'll use molarity and identify the item in here that's going to help me get into the pH square. Since it's asking for the pH of the solution, the thing that I'm going to want to find is the H3O plus ion concentration. And so to start with, we're told that we have a 0.165 molar solution. None of this, none of this, and none of this. And we start with 0 and 0 of this because it doesn't tell us that there's any in that solution to start with. I'll lose X amount of this and gain X amount of both of these, and so I end up with 0.165 minus X and X's of each of those. Setting this equal to the equilibrium constant, which is 3 times 10 to the negative 8th, this is equal to X squared, or X times X, divided by 0.165 minus X. I'll ignore this X because it's small compared to the 0.165. Because this is a weak acid, only a very small amount of it dissociates, and I can ignore that to make this problem a lot easier to solve. I'll now solve for X, and this X will give me the H3O plus ion concentration, and then I can take the negative log of that to find the pH. I'm going to leave the rest of that for you to solve. On to part B, it now says that I calculate the value for the pH when there's 14.3 grams of calcium hypochlorite. So the OCl minus, the anion of the acid, came together with calcium to make a salt. And it's dissolved in 1 liter of the solution, and it gives me a hint, careful, there are 2 OCl minus ions in each one of these. And so the first thing, once again, in the order of event or problems, identify the weak acid or base. We already identified the weak acid in the letter A, and so that's the same thing that I'll use here, HOCl. Once again, when in doubt, react it with water, and I'll end up with the same equation where I get H3O plus and some OCl minus. And once again, the thing that I'll be interested in is the thing that'll get me into the pH square. And of course, to find out the pH here, I can use the H plus ion concentration, which is right here. Ice table that guy, but I'm going to leave a lot of room here because I'm going to have some converting to do. And so in this case, I'm told that I have a HOCl solution that is in 1 liter, and I have 0.165 molar solution, or 0.165 moles of it. Where do I get the number of moles? Remember that molarity is equal to moles divided by liters, and I'm told that the molarity in the problem is 0.165 molar. So I take 0.165 times 1 because I'm told that there is 1 liter of the solution right here in the problem. And that gives me a number of moles. Water, of course, is a pure liquid and is not going to be involved in the equilibrium constant expression, so I can ignore that. There's none of this to start with, but there is some of this. And this happens to come from the salt that's dissolved in there. And if I go back and quickly reread the question, notice there's some CaOCl2 that's dissolved in the solution. And so the CaOCl2 is going to completely dissociate to give me some Ca++, which will simply spectate because that came from a strong base. And remember, anything from a strong base is going to do nothing as far as pH goes in the solution. And it will give me 2 OCl minuses. And so there is a 1 to 2 ratio of those dissolved in solution. So to find out the number of moles of this that are in the solution to start with, I need to take the amount of grams that I have of this, which is 14.3 grams. Going back and rereading the question again, remember it said there's 14.3 grams of this dissolved. Convert it to moles, and remember that there are in 1 mole of CaOCl2 143 grams. Where did I get that? I added up 1 Ca and O, 2 O's and 2 Cl's on the periodic table. And then the tricky part of this is to notice, and they give you a hint in the question, that notice there are 2 OCl minus ions in each one of these. So I need to make a ratio that for every 1 of these moles of CaOCl2s, there are 2 OCl minus ions. And of course that's the thing that I'm interested in, because this has a fancy name. This is the conjugate base of this weak acid right here. So once I do that math, I end up with 0.2 moles of the OCl minus. So now if I'm a good recognizer, I can see that I have moles of a weak acid and I have moles of its conjugate base. And if you forgot the definition of this, something that has a weak acid and its conjugate base, or a weak base and its conjugate acid, is called a buffer. If you know this, you can jump right to the Henderson-Hasselbalch equation, or you can do what we did up above and set it equal to the K expression. K is equal to 3e to the negative 10th, and this is equal to my products, which of course would be 0.2 plus x, because remember I'm going to gain x and gain x here, I'll end up with x here, and this would be 0.165 minus x, 0.165 minus x. I'm going to ignore these x's though because they're small compared to the 0.2 and the 0.165, and I would end up with products 0.2 times x divided by 0.165. And I could solve for x to get me the H3O plus ion concentration, just like I did in the first problem. Conversely, I could just jump to the Henderson-Hasselbalch equation, where the pH is equal to what's called the pKa plus the log of the base, 0.2, divided by the acid, 0.165. You'll notice it ends up being a similar equation to what we have up above here, except I have to find what's called the pKa, and remember the pKa is just the negative log of the Ka, and the negative log of the 3 times 10 to the negative 8th ends up being negative log of 3.8 ends up being, I think I have to do that on my calculator here really quick just to make sure of it. Negative log, and my Ka is 3 enter exponent to the negative 8th, 7.52. So this ends up being 7.52 for the pKa plus the log of 0.2 over 0.165. So do this part on your calculator first, 0.2 divided by 0.165. I end up with that number, and then take the logarithm of that. So log of second answer, and then add that to the 7.52, and I find out that my pH is equal to 7.6. So pH of this buffer solution is equal to 7.6. So that helps answer letter B, and then in letter C says, would the value of H3O plus increase, decrease, or stay the same in the buffer solution if a small amount of KOH was added to 1 liter of the solution? Justify your answer with an equation. Well, since we know that this equilibrium contains a weak acid and also its conjugate base, when we add some KOH, remember KOH is a strong base, right? Strong bases are the lithium, sodium, potassium, rubidium, cesium hydroxide. When we add this strong base, it's going to want to react with the acid portion of the buffer. So the base and the acid portion of the buffer are going to react. And it says it's a small amount of this. So my equation would have to be the KOH plus the weak acid portion of the buffer. Acids, of course, give away a proton, so we'll end up with some HOH, and then we'll end up with some KOCl over here, Cocal. And from this, of course, we would use up some of this, but not very much, and of course the base would be all gone, since it said there's only a little bit of it, and therefore we'd only be adjusting this ratio right here a tiny, tiny bit. And therefore we would not change the pH very much at all, because we'd be only using up a little bit of the weak acid to make that happen. Okay, moving on to number 2. Number 2 asks about acid called benzoic acid, and it gives us some data right here. And it says calculate the pH of a buffer solution that's 0.1 in benzoic and 0.1 in sodium benzoate. Now, you might not know the formula for sodium benzoate, but it doesn't really matter, because all you need to know is that there's this acid. It's a weak acid. It's called HA. This is the anion. They actually give you the formula for the acid as C6H5CO2H. Here's the H. That's right here. And then, of course, sodium benzoate would just be this anion, C6H5CO2, and then it would have an Na stuck on it instead of the H. So that's my acid, and this right here would be the conjugate base of this acid that came from a sodium salt of the acid. So once again, using the order of events for the problems, identifying the weak acid and base is probably the trickiest part, because you're just unfamiliar with these anions. But as you become more familiar with them, just realize that, hey, the acid has the H on it, and then if you're going to have a base from it, it's going to have the anion, and it's going to have some kind of positive thing attached to it. Probably something that makes it soluble. And if you remember from your solubility rules, any alkali metal cation is going to always be soluble. And so that's why salts of lithium, sodium, potassium, rubidium, and cesium are very popular, because anything that's attached to this group right here is going to be soluble in water. So now that we've identified the weak acid and base, we can write the equilibrium of the weak acid or base with water. So take your weak acid. I'm just going to write it as HA, because it's a lot easier to write instead of this whole big thing. React it with water. And then what we're going to get is the acid donating a proton to give us H3O+, and then A-. And in this case, it tells us that it's a buffer solution, and it's 0.1 molar in benzoic acid and 0.1 in the sodium benzoate. So initially, there's 0.1 moles of this, and there's 0.1 moles of this anion right here, or the conjugate base. You can write that down to just get used to calling it the conjugate base, because that's what the leftover anion, or the piece that remains after the acid is released as proton, is always called as the conjugate base. So knowing this, I can immediately just make an ice table and do my lose x, gain x, gain x, gain x, and solve for this. Or maybe alternatively easier, I could jump to the Henry-Hasselbalch equation. And this is where pH is equal to the pKa plus the log of the base over the acid. So I need to know the pKa, and remember the pKa is simply the negative logarithm of the Ka. In this case, the Ka is 6.3 times 10 to the negative 5th, and plus the log of the base is 0.1, and the acid is 0.1. Oh, look at that, 0.1 divided by 0.1 is 1, and the log of 1 is, yep, 0. So really, the pH is going to be equal to whatever this negative log is. In other words, the pH is equal to the pKa. Okay. Well, it turns out the negative log of 6.3 times 10 to the negative 4th is 4.2. And so my pH is equal to 4.2, which is also my pKa, which I have written right here. This is going to be helpful because I'm going to use that in the next part of the problem, part B. In part B, it says calculate the pH of a buffer solution that's now 0.2 molar in benzoic acid, and it's 0.05 in sodium benzoate. So now I have the same equilibria, except for this time it's not 0.1 here, it's 0.2 molar in benzoic acid. And then secondly, it is 0.05 in sodium benzoate, 0.050 molar right here. So we have 0.2 and 0.05. All right, well, now we could take these values and we can put them into the Henderson-Hasselbalch equation, especially since we know the pKa of it, and it makes the calculation really easy rather than doing the full ice table. So in letter B, I do pH is equal to 4.2, because remember that's the pKa, plus the log of the base, which is my 0.05 molar, divided by my acid, 0.2. I'm going to leave this part for you to work, and you can come up with what the pH is by punching the buttons on your calculator, and you can figure out how the pH would change now that we've added this salt to this equilibrium, or the conjugate base portion as well. In letter C, it says calculate the number of grams of sodium benzoate that must be added to 750 milliliters of a 0.2 molar benzoic acid to make the buffer solution have a pH of 4. So there's a couple of different ways to approach this, but following our order of events, the first thing, of course, is to identify the weak acid or base. We did that up above in the first part of 2. We have this thing called benzoic acid. When in doubt, react it with water, and then over here we're going to get our H3O plus and our A minus. So we've done the step 1 and the step 2 of identifying the weak acid or base and writing the equilibrium of the weak acid or base with water. Now we could go ahead and ice table it, but notice that it tells us right here it's a buffer solution. If it's a buffer solution, we can immediately jump to the Henderson-Hasselbalch equation, which remember is pH is equal to pKa plus the log of the base over the acid. In this question, it says calculate the number of grams of sodium benzoate. Remember, sodium benzoate from up above is the salt right here, or the conjugate base containing salt of benzoic acid. And so if we know that this sodium benzoate is the conjugate base, it fits right here in the Henderson-Hasselbalch equation. That's the thing they want us to know, is how many moles of that base, actually how many grams of that base need to be added. We'll find moles first and then go to grams. The other information is given to us in the question, or we can calculate it. First of all, the pKa we know from up above in B and in A. That's equal to 4.2, and then it's plus the log of the base, which we're looking for, over the acid, and it says that it is a 0.2 molar benzoic acid solution. Now the mathematics on this is a little tricky, so I'm going to set up a bunch of it, and then I'm going to have you work the rest of it. But let's plug in the numbers, because we know the pH, it says in the question, would be equal to 4. And so we end up with a math equation that is 4 is equal to 4.2 plus the log of B over 0.2. Now you might or might not remember from your math class that when you have a log of one thing divided by another, you can also write this as the log of B minus the log of the thing on the bottom, 0.2. Now that I've separated it that way, you can go ahead and you can calculate this part on your calculator. Notice there's a minus sign right there. Don't lose that negative, or else you'll be sad. You can keep the log of B by itself, and once you've calculated these, you can bring them to the other side. And then the mathematical function for this, remember, is to undo the log, because you'll end up with the log of B equaling some number over here, is the 10 to the x key on your calculator, and then you'd put this number in right here. I'll leave the remainder of the math for you, but at least you have it set up and you can move from there. Let's go on to number 3, the very last problem on the worksheet. And on this one, they say, in blood, bicarbonate and carbonic acid form an important buffer. The Ka of carbonic acid's first association is, and here's the Ka, and they also give you the pKa right here as well. Then they say, calculate the pH of this that has a concentration of bicarbonate and carbonic acid that are equal to each other. Equal to each other. So we end up with another question about buffers. And of course, we've got two things in here. We've got carbonic acid, and we've got the sodium bicarbonate. Bicarbonate is HCO3-. And as you can see, here's our weak acid. And then this thing has a sodium ion in it that we can ignore, but we've got the HCO3- ion that is called our conjugate base. So we have a weak acid conjugate base pair here, which makes it be a buffer. And once you become a little more skilled at these, you can jump right away, if you have to find the pH or something that's in the equation, of pH is equal to pKa plus the log of base over acid. Now they tell us to calculate the pH of this when there's an equal amount of base and acid. Of course, if this number is equal to this number, this now becomes the log of 1. And the log of 1 is 0. So in other words, the pH of this solution would be equal to the pKa, and lo and behold, they tell us the pKa right here in the question, 6.35. There's my pH. Now, in letter B, they say that the ratio of HCO3 and H2CO3 is now 16. What's the pH? So it's handy to have that ratio, because guess where you see the ratio of base over acid? Yep, you find it right here in the Henderson-Hasselbalch equation. And so if you know the pKa is 6.35, then you can take the log of the base. Remember, the base is the HCO3-, and the acid is H2CO3. And it says this ratio is equal to 16. And so you can plug this number in right